All right, let's get into it. Today, we're going to unpack one of the slickest, most elegant ideas in all of machine learning, the support vector machine kernel trick. You know, SVMs are amazing, but they run into this huge wall with nonlinear data. We're going to see how they solve what looks like an impossible problem, all thanks to this brilliant mathematical hack. So, let me ask you this. How do you solve a problem that seems, impossible? I mean, what do you do when you hit a wall? In machine learning, this happens constantly, especially when you're trying to classify data that's just a complete mess, all jumbled together. And that right there, that's the core challenge that gave birth to the kernel trick. Okay, so section 1, the non-linear challenge, or as the slide says, when a straight line isn't enough. See, the whole point of a support vector machine, its bread and butter, is finding the perfect straight line, or, a flat plane if you're in more dimensions, to split two groups of data. But what happens when you can't? What if your data points are all mixed up and there's just no way to draw a simple line through them? And this isn't some abstract math problem, right? This is the real world. Think about image recognition. Pixels are never that neat. Or bioinformatics, trying to make sense of incredibly complex genetic data. The world is just messy. So to make this real, just take a look at this sample data. We've got two features, A1 and A2, and then a label, Y, which tells us if a point belongs to group 1 or group 0. Now, you don't even have to be a data scientist to see the problem here. If you tried to plot these points on a graph, you'd realize right away there's no single straight line you can draw to cleanly separate the ones from the zeros. They're all tangled up.
Okay, next up, a higher dimensional idea, the search for linearity. So this problem leads to a really wild, kind of out there idea. What if we could take our messy 2D data and just pop it up into a higher dimension, like a third dimension or a fourth, or even higher? The hope, the dream, is that in this new space, the data would sort of magically untangle itself. And suddenly, it would be linearly separable. We could just slice a simple plane right between the two groups. Problem solved, right?
Well, to pull that off, you'd need some kind of special function, a transformation function. In the math world, we call it phi of x. And its whole job, its only purpose, is to take our original data points from that messy space and map them or project them into that shiny new higher dimensional space where everything is nice and clean and linear. Sounds amazing in theory, doesn't it?
Which brings us to our next section, the transformation roadblock. Or to put it simply, finding phi of x is hard. Yeah, because while that idea of a transformation function is super powerful, actually figuring out what that function is, that's a whole other story. And here's the big but. The problem is, for any real-world dataset that's even a little bit complex, figuring out the exact formula for that phi of x function is, it's incredibly hard. In a lot of cases, it's literally impossible. So it seems like we've hit a dead end. Are we just stuck? Well, what if we've been asking the wrong question? What if we don't actually need to find the function at all? This is where the whole thing gets so incredibly clever. What if there was a way to get all the power of that higher dimensional space without ever having to define the function, and without ever actually going there?
So this leads us to the inner product secret, what the algorithm really needs. See, to understand how this is even possible, you have to know a little secret about how the SVM algorithm actually works under the hood. It turns out it doesn't need as much information as you'd think. It has one very specific need, and that one detail changes everything. And this quote from the source material absolutely nails it. It says, "The learning algorithm only needs the inner products of the observations." Now think about what that means. The SVM algorithm doesn't actually care where the new points are in that high-dimensional space. It doesn't need their coordinates. Nope. All it needs to do its job, all it needs to find that perfect separating line, is the inner product, which you probably know as the dot product, between pairs of those transformed points. And the best part is, an inner product is a super simple calculation. Let's just grab two of our original data points, x1 and x2 from the table earlier. To get their dot product, you just multiply the first numbers together, then multiply the second numbers together, and add the results. So you've got 2 times 2 plus 4 times 7, and that gives you 32. That's it. The SVM algorithm just needs a whole bunch of these simple little numbers to work its magic. And that brings us to the big reveal, the kernel hack, bypassing the transformation. That little detail we just talked about, that the algorithm only needs the inner product, that's the loophole. That's the exact opening that the kernel trick exploits to completely sidestep the whole impossible problem of finding that phi of x function. So here's how it works. We introduce something called a kernel function, which we write as k of xi xj. And you can just think of this function as an amazing shortcut. It's a special function that takes two data points from our original messy low-dimensional space, and it directly computes the answer to the question, what would the inner product of these 2 points be if we had transformed them into that higher dimensional space? It gives us the answer without ever doing the hard work. And that's why we call it a hack. I mean, it is a clever mathematical hack. It's this beautiful, elegant way to give the SVM algorithm the exact number it needs without going through any of the pain of actually transforming the data. It's just so efficient. And this slide just lays it out so perfectly. Look at the difference. The hard way, on the left, is this painful 3-step process. First, you have to somehow find that crazy complex phi function. Then you have to transform every single one of your data points, and only then can you calculate the inner product. But the kernel way, it's so much simpler. You just pick a standard kernel function, there are a few common ones to choose from, you feed it your original data points, and boom, you get the result directly. It's not even a contest. So if you remember one thing, let it be this. The crucial point of the kernel trick is that it lets our algorithm get all the benefits of operating in a higher dimension without ever actually going there. It's like getting the view from the top of the mountain without having to do the climb. You get all that amazing separation power, but you never have to pay the massive computational price of actually transforming your data into some infinitely complex space. It's just a brilliant, indirect approach. And that really just leaves you with a final thought, doesn't it? The kernel trick is such a perfect example of the kind of mathematical ingenuity that powers so much of AI. It's not always about brute force. Sometimes it's about finding a clever shortcut. It really makes you wonder, what other amazing hacks like this are out there, humming away under the hood, quietly making the impossible possible in the AI we use every single day?